Good day, everyone. Welcome in Physical Science. Now we'll be having first our pretest. So direction: choose the letter of the best answer and write the chosen letter on a separate sheet of paper. Number one, it is a device that is used to speed up the protons to overcome the repulsion between the protons and the target atomic nuclei by using magnetic and electrical fields. A. Spectroscopy. B. Particle decelerator. C. Particle accelerator. And letter D. Microscope. Alright, the answer for number one is letter C. Particle accelerator. Number two, he created a classification of elements based on their atomic weight. A. Ernest Rutherford. B. John Dalton. C. Robert Millikan. D. Dmitry Mendeleev. The answer is letter D. Dmitry Mendeleev. Number three, it is a one-dimensional point which contains a huge mass in an infinitely small space. A. Nucleosynthesis. B. Dilation. C. Singularity. D. R. Process. The answer is letter C. Singularity. 4. He noticed that shooting electrons at elements caused them to release X-rays at unique frequencies. A. Dmitry Mendeleev. B. Robert Millikan. C. Henry Mosley. D. Emilius Serge. The answer is letter C. Henry Mosley. 5. He synthesized elements with atomic number 43 using a linear particle accelerator. A. Ernest Rutherford. B. Ernest Lawrence. C. Dmitry Mendeleev. D. John Dalton. The answer is letter B. Ernest Lawrence. Number 6. This is known as the origin and production of heavy elements. A. Stellar nucleosynthesis. B. Primordial nucleosynthesis. C. R process. D. Supernova nucleosynthesis. The answer is letter A. Stellar nucleosynthesis. For number 7, this is also known as origin of light's elements. A. Stellar nucleosynthesis. B. Primordial nucleosynthesis. C. R process. D. Supernova nucleosynthesis. The answer is letter B. Primordial nucleosynthesis. 8. The process that can produce elements up to bismuth or atomic number 83. A. Nuclear fission. B. R process. C. S process. D. Stellar nucleosynthesis. The answer is letter C. S process. 9. This is also known as nucleosynthesis. A. S process. B. R process. C. Nuclear fission. Letter D. Proton-proton reaction. The answer is letter C. Nuclear fission. 10. This occurs in the main sequence of stars. A. Stellar nucleosynthesis. B. Primordial nucleosynthesis. C. R process. D. Supernova nucleosynthesis. The answer is letter A. Stellar nucleosynthesis. 11. It is also known as nuclear fusion and the formation of the new nuclei actions in the early stage of development of the universe. A. Nucleosynthesis. B. S process. C. R process. D. Singularity. The answer is letter A. Nucleosynthesis. 12. In this process, there's a buildup of very heavy isotope. Then, as beta decays occur, you march up in an atomic number and produce heavy product. A. S process. B. R process. C. Nuclear fission. Letter D. Proton-proton reaction. The answer is letter B. R process. 13. he successfully carried out a nuclear transmutation reaction, a process of transforming one element or isotope into another element. A. James Chadwick. B. Henry Mosley. C. Dmitry Mendeleev. D. Ernest Rutherford. The answer is letter D. Ernest Rutherford. 14. It was created by a bombardment of molybdenum by deuterons heavy hydrogen H12 by Emilio Serge and Carlo Perrier in 1937. A. Oxygen. B. Helium. C. Technetium. D. Uranium. The answer is letter C. Technetium. 15. These are elements with atomic numbers beyond 103. A. Super heavy elements. B. Gaseous elements. C. Lightest element. D. Halogens. The answer is letter A. Super heavy elements. Today we are going to discuss with you concept of atomic number that led to the synthesis of a new elements in the laboratory. Now for our objectives, after going through this lesson you are expected to 1. Explain how the concept of atomic number led to the synthesis of the new elements in the laboratory. 2. Identify the different elements formed after the process of synthesis. 3. Realize the importance of the atomic number in identifying the new element's identity in the periodic table. The atoms that make up the elements are further composed of tiny particles, the neutron, proton, and electron. Hydrogen and helium are the elements that exist in the early beginning of the Big Bang. As the universe expanded and cooled, there was a period of proton-proton chain reaction wherein protons fused into helium. Red giant cores get deposited this via the triple alpha process. But the universe expands right through this possibility, and the density, temperature are quickly too low to support synthesis of any additional elements. You learned earlier how all matter in the universe is made from tiny building blocks called atoms. All modern scientists accept the concept of the atom, but when the concept of the atom was first proposed about 2,500 years ago, ancient philosophers laughed at and opposed the idea. It has always been difficult to convince people about the existence of things that are too small to be seen. We will spend some time considering the evidence or what we call observations that help convince scientists of the existence of atoms. Do you have any idea how the different elements in the periodic table were formed, known, and identified? Let's have a short review. There is what we call Big Bang theory that has some points, stages. 1. Singularity, inflation, nucleosynthesis, and recombination. Let us differentiate them. 1. Singularity. It is one-dimensional point which contains a huge mass in an infinitely small space where density and gravity become infinite and space curves infinitely, and where the laws of physics as we know them cease to operate. The basic homogeneity in distribution of matter in the universe was established as a consequence of the first phase of inflation. Now, when you say singularity, it is a model of the universe which makes the striking prediction that the universe began a finite amount of time in the past. Now, when you say finite amount of time in the past, this calling something finite means it has an end or finishing point. Nucleosynthesis was the nuclear fusion and the formation of new nuclei atoms in the early stages of development of the universe. Recombination, the formation of the capture of free electrons by the cations in a plasma. These fusion reactions can be two or more nuclei to form new nuclei of atom. It focuses on the process that creates new atomic nuclei from pre-existing nucleons, and these nucleons, the protons and neutrons, and the nuclei. The first will be having an activity, making your own periodic table. So make your own periodic table for A and B using the hypothetical elements that are given clues. Explain the words that will be formed if you arrange the symbols of the elements correctly. So we have letter A, P have one electron each. B, O, D, R, I, and E are in the same series as P, C, and I. In terms of atomic size, P is the biggest while C is the smallest. E is a metal while I is a nonmetal. OD is smaller than Ri in atomic size. And for letter C, arrange the letters and find the hidden word. Here are the key points. Number one, the atomic number is the number of protons, positively charged particles, in an atom. In 1913, Henry Gwen Jeffreys Mosley was an English physicist who demonstrated that atomic number, the number of protons in an atom, determines most of the properties of an element. In 1919, Ernest Rutherford successfully carried out a nuclear transmutation reaction, a process of transforming one element or isotope into another element. In 1925, there were four unknown elements in the periodic table that corresponds to atomic numbers 43, 61, 85, and 87. Elements with atomic numbers 43 and 85 were synthesized using particle accelerators. A particle accelerator is a device that is used to speed up by protons to overcome the repulsion between the protons and the target atomic nuclei by using magnetic and electrical fields. It is used to synthesize new elements or forming new elements. And this is what we call particle accelerator. A particle accelerator is a machine that uses electromagnetic fields to propel charged particles to very high speeds and energies, and to contain them in a well-defined beams. Large accelerators are used for basic research in particle physics. Elements with atomic numbers greater than 92, atomic number of uranium, are called transuranium elements. They were discovered in the laboratory using nuclear reactors or particle accelerators. Dmitry Mendeleev created a classification of elements based on their atomic weight. He found out that organizing the elements at the time by their calculated weight demonstrated a periodic pattern of both physical and chemical properties, such as luster, physical state, reactivity to water, and others. Now, for your activity 1.1, making your own periodic table shows how theoretical elements were arranged according to their atomic weights. For example, hydrogen has atomic mass of 1.00794 atomic mass unit, which makes hydrogen the lightest element on the periodic table. Hydrogen, or the symbol is big letter H, was named by Lavoisier and is the most abundant element on the periodic table. It is followed by helium, lithium, and beryllium, and so on and so forth, because atomic weight is used to arrange the elements from lightest to heaviest. By the way, who is Henry Mosley? He was an English physicist, and his experiment demonstrated that the major properties of an element are determined by the atomic number, not by the atomic weight, and firmly established the relationship between atomic number and the charge of the atomic nucleus. Henry Mosley was a researcher at Rutherford's laboratory. In 1913, Mosley used Ernest Rutherford's findings to advance understanding of the elements and solve the problem with Mendeleev's periodic table. Mosley noticed that shooting electrons at elements caused them to release X-rays at unique frequencies. He also noticed that the frequency increased by a certain amount when the positive charge of the chosen element was higher. By arranging the elements based on the square root of the frequency that they emitted, he was able to arrange the element that approximates their observed properties as proposed by Mendeleev. Henry Moseley proposed that elements' atomic number or place in the periodic table was uniquely tied to their positive charge or the number of protons they have. So this discovery allowed to a better arrangement of the periodic table and predicted elements that were not yet discovered. His method of identifying elements by shooting electrons and looking at X-rays became a very useful tool in characterizing elements and is now called X-ray spectroscopy. He used spectroscopy to determine the atomic number of an element. He bombarded a beam of electrons to different elements and measured their X-ray spectral lines. These results clearly show that frequency of the X-rays given off by an element was mathematically related to the position of that element in periodic table. The frequency is proportional to the charge of the nucleus or the atomic number. When the elements were arranged according to their atomic numbers, there were four gaps in the table. These gaps correspond to the atomic numbers of 43, 61, 85, and 87. These elements were later synthesized in the laboratory through nuclear transmutations. Discovery of nuclear transmutation. In 1919, Ernest Rutherford successfully carried out a nuclear transmutation reaction, a reaction involving the transformation of one element or isotope into another element. The first nuclide to be prepared by artificial means was an isotope of oxygen, oxygen 17, atomic weight of 17. It was made by Ernest Rutherford in 1919 by bombarding nitrogen atoms with particles. So take a look on this. So we have nitrogen 14 atomic weight and we have atomic number 7 plus, okay, alpha particle which is atomic number 2 and atomic weight 4. Then oxygen we have 17 and 8, atomic number 8 plus hydrogen. Right? So we'll be having here nitrogen plus alpha particle injection. It will produce oxygen plus hydrogen. So we have atomic number first, 7 plus 2 equals 9. 8 plus 1 equals 9 for atomic number. And for the atomic weight, 14 plus 4 equals 18. And 17 plus 1 equals 18. And this is the reactants and this is the product. Make sure it's equal. However, both alpha particles and atomic nuclei are positively charged, so they repel each other. Therefore, instead of using fast-moving alpha particles in synthesizing new elements, atomic nuclei are often bombarded with neutrons, or this is what they call neutral particles, in particle accelerators. James Chadwick discovered the neutron in 1932 as a previously unknown neutral particle produced along with carbon-12 by the nuclear reaction between beryllium-9 and helium-4. Now, we have beryllium, atomic number of 4 and atomic weight of 9. So we plus alpha particle, which atomic number of 2 and atomic weight of 4, then it will produce carbon plus neutron. So we have here 4 plus 2 is 6, and of course we have the neutron atomic number is 0. 9 plus 4 is 12, and of course we have here 12 plus 1 13. 9 plus 4 is 13, so it's equal. The first synthesized element that does not occur naturally on the Earth, technetium, was created by bombardment of molybdenum by deuterons, heavy hydrogen, or we have hydrogen 2, atomic weight of 2 and mass number of 1 by Emilius Segre and Carlo Perrier in 1937. So like for example here, we have hydrogen atomic number 1 and mass weight or atomic weight 2 plus molybdenum. So we have atomic number 42 plus mass weight of 97. Then we have 2 neutron here plus technetium. We have 2 times 0, that would be 2 plus 43, that would be 43. So 42 plus 1, 43. And we have 97 plus 2, 2 times 1 is 2. We have 99, so 2 plus 97 is 99. The first controlled nuclear chain reaction was carried out in a reactor at the University of Chicago in 1942. One of the many reactions involved was 12 uranium 92235 plus neutron, so 1 0. We have bromine, deuterium plus 3 neutron. So we have here 92 plus 0 x, it produces 2 heavy nuclei, 35 and 57, and of course plus 0 here, neutron, that will be 92. So we have 235 uranium, so plus 1 neutron, and of course we have 87 plus 146 plus 3, that will be 235. The discovery of the missing element recalled that in 1925 there were 4 vacancies in the periodic table, corresponding to the atomic numbers 43, 61, 85, and 87. Two of these elements were synthesized in the laboratory using particle accelerators. Particle accelerator is a device that is used to speed up the protons to overcome the repulsion between the protons and the target atomic nuclei by using magnetic and electrical fields. It is used to synthesize new elements. In 1937, American physicist Ernest Lawrence was also able to synthesize element with atomic number 43 using a linear particle accelerator. He bombarded molybdenum, which is Z equals 42, which with fast-moving neutrons. The newly synthesized element was named technetium, or the Tc, after the Greek word technetus, meaning artificial, or Tc was the first man-made element. The bombarding of molybdenum with deuterium formed technetium, which is the first artificially made element. Now here, so we have molybdenum, atomic number 42 and 97 plus hydrogen 1 and 2. So it will produce technetium and neutron. In 1940, Dale Carson, K. Mackenzie, and Emilio Segre discovered element with atomic number 85. They bombarded atoms of bismuth, 83, with fast-moving alpha particles in a cyclotron. A cyclotron is a particle accelerator that uses alternating electric field to accelerate particles that move in a spiral path in the presence of a magnetic field. Element 85 was named astatine from the Greek word astatos, meaning unstable. The two other elements with atomic numbers 61 and 87 were discovered through studies in radioactivity. Element 61, the promethium, was discovered as a decay product of the fission of uranium, while element 87, francium, was discovered as a breakdown of the product of a uranium. The other one is a decay, the other one is the breakdown product. The synthesis of the elements. The inventions of cyclotron paved the way of for artificial transmutation of one element into another. The high energy particles produced by cyclotron produced heavier nuclei upon hitting heavy target nuclei. The universe run into the P problem. Red giant cores get past this by the triple alpha process, but the universe expands right through this possibility, and the density temperature are quickly too low to synthesize any additional elements. Big Bang nucleosynthesis. The oldest stars in the galaxy are deficient in elements heavier than helium. 2. The current record holder has iron and hydrogen about 130 times smaller than the solar value. Not quite down to Big Bang abundances, but we are getting pretty close and still looking. We have the chemical evolutions of the universe. So, chemical evolution 1. Low mass stars synthesize new helium, carbon, and oxygen during the main sequence or RGB, HB, and AGB process. These newly produced elements are brought to the surface via convection and redistributed via stellar winds and planetary nebulae into the interstellar medium to be incorporated into later generations of stars. So we have here, this is the main sequence star, RGB, HB, and AGB phases. So when we say RGB stands for red giant branch, and we have HB, horizontal branch, and we have AGB, asymptotic giant branch. So take a look on this picture. A star remains on the main sequence as long as there is hydrogen in its core, that it can fuse into helium. So far, we have assumed that a star on the main sequence maintains a constant energy output. In fact, as a main sequence star ages, its luminosity increases slightly, resulting in it expanding and its outer layer cooling. This explains why the main sequence is a broad band rather than a narrow line. Stars move up and to the right on this band as they age. Eventually, the hydrogen fuel in the core runs out and fusion stops, shutting off the outward radiation pressure. Inward gravitational attraction causes the helium core. This is the helium core to contract, converting gravitational potential energy into thermal energy. Although fusion is no longer taking place in the core, the rise of the temperature heats up the shell of the hydrogen surrounding the core until it is hot enough to start hydrogen fusion, producing more energy than when it was a main sequence star. This cold shell burning causes some interesting effects. Another one is the alpha triple alpha process. So we have here, so alpha particle, alpha particle. So helium 4, 2, atomic number of 2, and mass weight of 4. The triple alpha process, or for post-main sequence stars, we have two helium nuclei. Oh, this is the alpha particles fused, all right, to form a beryllium 8 nucleus. This is unstable and normally decays back into two, okay, hydrogen 4 electrons nuclei within a fraction of a second, but given the high number of helium-4 nuclei in the core, will sometimes collide with one before it had a chance to decay. All right, so here again we have two alpha particles and fused together and produce beryllium 8. And then when beryllium 8 fuse to helium, another helium or alpha particle, then it will produce carbon 6 or carbon 12 atomic weight and atomic number of 6 through the energy of gamma ray photon. And if again carbon 612 fuse to another helium particles, then it will produce oxygen 8 16 through gamma ray photon. And this is what we call the triple alpha process or the helium fusion. Chemical evolution 2. For more massive stars, equilibrium fusion reactions produce elements all the way up to iron. Freshly made elements are delivered via stellar winds or sometimes more spectacularly via supernova explosions. Chemical evolution 3. What about the trans iron elements? Equilibrium fusion reactions of the light elements don't proceed past iron because of the iron's location at the peak of the curve of binding energy. However, in a certain circumstances, supernova, for example, non-equilibrium reactions can be built up beyond iron in the periodic table. Many of these are radioactive, but some are stable. Neutron capture elements. There are two principal paths to building the elements heavier than iron. Both use the addition of neutrons to existing seed nuclei. Neutrons have no charge, so are much easier to add to positively charged nuclei. S process, slow addition of neutrons. The R process, rapid additions of neutrons. The S process stands for a slow addition of neutrons to nuclei. The addition of the new produces heavier isotope of a particular element. However, if an electron is emitted, this is called beta decay. The nucleus moves one step up in the periodic table. Slow here means that rate of new captures is low compared to the beta decay rate. It is really it really is low. Sometimes hundreds of years go by between neutron captures. Now we have here iron 56 plus neutron, that would be iron 57, atomic weight 57. And we have iron 57 to cobalt 57 plus negative electrons. Here are neutron changes in a proton by emitting an electron. So the S process can produce elements up to number 83, bismuth. There are peaks in the solar system's abundance of heavy elements at 38 strontium, 56 barium, and 82 lead. These are easily understood in the context of the S process and the magic numbers of neutrons. The site of the S process is the AGB star during the between shell flashes. The no source is a byproduct of carbon-13 and helium-4 is oxygen-16. The 43 or technetium is an S-process nucleus and the proof that it is in operation of AGB stars. The R process. The R process is the rapid additions of the neutrons to existing nuclei. Rapid here means that main neutrons are added before a beta decay occurs. First build up a very heavy isotope, then, as beta decays occur, you march up the atomic number and produce the really heavy stuff. A big burst of neutrons is needed for the R process to occur. The most promising place with the right conditions is in an SN2 explosions right above the collapsed core. Now, like for example, this one. So here we have diagram one. So the R process occur, and this is what we call the crab nebula. The transceramic elements. In 1930s, the heaviest element known was uranium with atomic number of 92. Early 1940, Edwin Macmillan proved that an element having an atomic number 93 could be created. He used a particle accelerator to bombard uranium with neutrons and created an element with an atomic number 93, which he named Neptunium. Transuranic elements are synthetic elements with atomic numbers higher than that of uranium 92. Now this is plutonium. At the end of 1940, element 94 was synthesized by Seaborg, Macmillan, Kennedy, and Wall. They bombarded uranium with the deuterium's particles composed of proton and neutron and a cyclotron. Element 94 was named plutonium. And this is the process made by Seaborg, Macmillan, Kennedy, and Wall. Elements with atomic numbers greater than 92 atomic number of uranium are called transuranium elements. Hence, Neptunium and plutonium are both transuranium elements. They are unstable and decay radioactively into other elements. All these elements were discovered in the laboratory as artificially generated synthetic elements. They are prepared using nuclear reactors or particle accelerators. In the next lesson, you will learn the nuclear reactions involved in the synthesis of these transuranium elements. Stellar nucleosynthesis. This process creates elements within stars by combining the protons and neutrons together from the nuclei of lighter elements. Fusion inside stars transforms hydrogen into helium, heat, and radiation. Heavier elements are created in different types of stars as they die or explode. The superheavy elements. Superheavy elements are elements with atomic numbers beyond 103. These are produced by bombarding heavy nuclear targets with accelerated heavy projectiles. Like, for example, the borium projectile used was chromium. So we have here bismuth plus chromium. Okay, it will produce borium with two neutrons. Following are the equations of several nuclear reactions that have important roles in the history of nuclear chemistry. The first naturally occurring and stable elements that was isolated or polonium was discovered by Polish scientist Marie Curie and her husband Betty in 1898. It decays emitting particles. So here we have polonium 84 and we have here it will produce lead plus alpha particles. And when alpha particles fuse together to lead, so that would be polonium, or it will form a new nuclei called polonium. Now, for your activity, write the nuclear reactions involved in the synthesis of each of the following new elements. A. Curium, or Z equals to 96, was formed by reacting Pu-239 with alpha particles. We have helium-4 atomic weight and 2 for atomic number, and it has a half-life of 160 days. B. Molybdenum, we have Z equals to 101, was formed by reacting En-253 with alpha particles. Neodymium, that is Z is equals to 109, was formed by cold fusion, which involves the combination of bismuth and iron nuclides at ordinary temperature. Another one, why do scientists study and synthesize new transuranium elements in the laboratory? And what are the uses of these elements? And of course, you are going to write a short essay, maximum of 3 sentences. So number one, Dmitry Mendeleev is often regarded as the father of periodic table. Would you say that Henry Mosley deserves recognition like him? Number two, explain why the atomic number is called the fingerprint of elements. Number three, how would you relate alchemy to synthesis of the new elements? Now for our assessment. Direction, choose the letter of the best answer. Write the chosen letter on a separate sheet of paper. So number one, he successfully carried out a nuclear transmutation reaction. It's a process of transforming one element or isotope into another element. A. James Chadwick. B. Henry Mosley. C. Dmitry Mendeleev. D. Ernest Rutherford. Number two, this is also known as nucleosynthesis. A. S process. B. R process. C. Nuclear fission. D. Proton-proton reaction. Number three, this is known as the origin and production of heavy elements. A. Stellar nucleosynthesis. B. Primordial nucleosynthesis. C. R process. And letter D. Supernova nucleosynthesis. 4. It was created by bombardment of molybdenum by deuterium's heavy hydrogen by Emilio Segre and Carlo Pérez in 1937. A. Oxygen. B. Helium. C. Technetium. D. Uranium. 5. Process that can produce elements up to bismuth. Atomic number 8. Now A. Nuclear fission. B. R process. C. S process. And D. S process. Number 6. This is known as the origin of the light element. A. Stellar nucleosynthesis. B. Primordial nucleosynthesis. C. R process. And D. Supernova nucleosynthesis. 7. It is also known as nuclear fusion and the formation of new nuclei actions in the early stages of development of the universe. A. Nucleosynthesis. B. S process. C. R process. D. Singularity. In this process, there is a buildup of very heavy isotope. Then a beta decays occur. You march up in the atomic number and produce heavy product. A. S process. B. R process. C. Nuclear fission. And D. Proton-proton reaction. Number 9. These are elements with atomic numbers beyond 103. A. Super heavy elements. B. Gaseous elements. C. Transition element. D. Halogens. 10. This occurs in the main sequence of stars. A. Stellar nucleosynthesis. B. Primordial nucleosynthesis. C. R process. And D. Supernova nucleosynthesis. It is a device that is used to speed up the protons to overcome the repulsion between the protons and the target atomic nuclei by using magnetic and electrical fields. A. Spectroscopy. B. Particle decelerator. C. Particle accelerator. And letter D, microscope. Number 12. He created a classification of elements based on their atomic weight. A. Ernest Rutherford. B. John Dalton. C. Robert Millikan. D. Dmitri Mendeleev. 13. It is one dimensional point which contains a huge mass in an infinitely small space. A. Nucleosynthesis. B. Dilation. C. Singularity. D. R. Process. Number 14. He noticed that shooting electrons at elements caused them to release X-rays at unique frequencies. A. Dmitri Mendeleev. B. Robert Millikan. C. Henry Mosley. D. Emilius Serge. 15. He synthesized the fourth third element using a linear particle accelerator. A. Ernest Rutherford. B. Ernest Lawrence. C. Dmitri Mendeleev. And D. John Dalton. Now for the answer for number one is letter D. Number two is letter C. 3A, 4C, 5C, 6B, 7A, 8B, 9A, 10A, 11C, 12D, 13C, 14C, and 15B. Now, for your additional activities, research on the latest instruments used in preparing new elements in the laboratory. What were the instruments used in preparing the newest four elements? Ionium, moscovium, tennessine, and oganesson. Thank you for listening.